So with that in mind, let's take a look at the experimental evaluation. So, we saw some exciting stuff, a little bit deflating to see the complexity results, but hey, they're DeepMind. They got the hardware for it, right? So training data, this was what I was talking about at the beginning. So training data consists of multiple triples, so multiple ILP instances for a given problem. And each step, one of the triples is sampled, and from the triple, they take a batch out of the positive and negative examples for that sample. And that's what they're using in a given batch. And they're saying in most cases, they're getting this done in 6,000 steps. They said cross entropy loss, as I showed you earlier, is what they used. They did try others. They didn't say what, I'm guessing mean squared error. They said the others worked pretty good too. That wasn't a huge deal. They used RMS prop with a learning rate of 0.5. They said Adam was good. They said it wasn't too sensitive to the learning weight, which actually I think is kind of good news there. And then clause weights were initiated from normal distribution over the 0, 1 interval. So these all seem pretty reasonable. I thought the training setup was kind of interesting. Now, I really like that they included this in the paper, which is why I put it verbatim. But they made a point that when they would learn the model, that they would suffer from local optimas a lot. And the good news is, though, is because of what they call the inductive bias of the model, which is the ability to generalize, all they have to do is out of like 100 runs, they just pick the one that has the lowest loss. And that kind of makes a lot of sense to me because remember, they're dealing with learning non-ground rules, which are going to be more general. They also are doing this thing with the training data where they're picking the constants. So different mini batches are using different constants, and they're kind of giving a little bit different view to push it toward certain predicates that tend to generalize more. And so because of that, they said, hey, when we pick the best one, it shows it works, ends up working very well. They also suggest that in future work, there could be things by inspecting the weights during training where you could just stop training after a couple of batches where it becomes obvious that, hey, it's heading towards that local optimum. But they didn't actually try that. They just didn't think this can be done. So one thing I want to show is difference between the various fuzzy T-norms that are used. And here we're looking at the percentage of runs with a very small mean squared error. And here in these problems, these are all like kind of very toy problems, like even odd is classifying digits as being even and odd. Less than is pretty obvious what that means. And then they have these kind of relationship things based on family tree and really tiny graphs looking at kind of graph problems like coloring and stuff. But bottom line here is what they list as differentiable ILP. This is using the product T-norm, and it's the best in almost every case. To demonstrate the robustness to noise is they then looked at analysis of mean squared error based on partial data. How did performance degrade as they reduce the size of the training set, as we see here? And actually, it still does fairly well, even when you get to around half the data before it degrades completely in many of these problems. So they're maintaining much of the performance. And this was one of the main points of the paper. The paper was very focused on, hey, this is an approach for noisy data. They didn't make the case that, hey, we're doing, neuro symbolic reasoning for the sake of it. This is actually, we're solving a real problem here, dealing with noisy data that not really addressed in the ILP literature at the time. So they did some tests. Everyone likes to show, hey, if we tack a CNN onto our method, then we can do something cool with it. But this one is a pre-trained CNN, so not really end-to-end training. Although the interesting thing about this is a way to induce extra noise into it. So they look at, again, a proportion of successful runs based on pairs held out from training, and also look at mean squared error, how that goes. So not too bad. I mean, looking at, you don't really start taking off with the error until you're hitting, 60, 70%, and with the baseline, it's already exceeding quite a bit early on.